and that is the derivative rule for inverses followed by the integrals for tan and cotangent. I'm actually going to do the integrals for tan and cotan first because they're easy, and all I need to do is show you where they come from and how they are calculated. They're pretty simple, pretty straightforward, and I'm guessing that most of you have already figured them out. And that is, I'm just going to do a quick u substitution for, instead of tan, I will be thinking of this as a sine over a cosine. As we've said in the past, whenever we're looking to do a u substitution, we want to u substitute the thing that is more trapped, the thing that is more contained. And most commonly, if I'm dealing with a fraction, that's usually going to be the denominator or the guts of the radical or the power. So I'm going to be going with a u substitution for the denominator here. And I'm going to let u be the cosine function. The derivative of u is therefore the negative sine function. I've got the sine function, but it's not negative, so I will replace the sine of x dx with a negative du. And so all of this stuff is going to be replaced with a negative du. And this thing right here will just become a u. And that makes the integral of a tan a negative ln of the absolute value of cos. Now the only big issue with that is that because my answer is a natural log, this negative that happens to be out in front has another alternative, another option, another way you could think of it. And that is as a cos to the negative 1 power. So if I were to take this cos and make it a, I don't want to do that. Make it a cos to the negative 1 power. Now that means that this is the equivalent or the same exact thing as the natural log of a secant that happens to be positive. Does that make sense? The inverse or the reciprocal of a cosine is a secant. And since we like to avoid negatives wherever possible, this is actually the one we're going to use more commonly, the ones your calculator will typically give you, and the one I'm going to ask you to memorize because it doesn't have a negative. Now, if you write that as your answer, the negative ln of cos, I'm going to give it to you. It's correct. It's just that the more you calculate with negatives, the more room you have for error. So avoid negatives wherever possible is something I've been preaching all year long. Questions, problems, amazing revelations. Now, likewise, and a little bit easier, you can imagine that the cotan function is going to work exactly the same way. I'm going to immediately change cotangent to the integral of cos over sine. I'm going to do a u substitution again, but this time I'm going to let u be the sine function. You're all being uber quiet. You don't want to be on the internet, huh? And that means the derivative is a very straightforward cos function. I don't need a negative in this one. So I'm going to go ahead and I'm going to replace cos x dx with a du. And I'm going to make that sine x be a u. And this one turns into a very straightforward ln of the absolute value of sine. And because this has a positive attribute, the way I see it, I can just memorize this one. It is worth noting, however, that just in case it were to show up on the AP exam, it is the same answer as a negative ln of the reciprocal function. I don't commonly see this one because I'm putting in a negative and a reciprocal function where I didn't need one, but it is the same answer. So if it were a multiple choice question on the AP and you were looking for the ln of the absolute value of sine of 3x and it wasn't there, but the negative ln of the cosecant of 3x was there, run with it. It's the same thing. Do you understand why? Pretty easy? Okay, 2 new integrals for you to memorize. Add them to your cheat sheet, and then flip backwards a page. This is my main focus for today, and it shouldn't take me more than 10 minutes. It helps a little bit if I familiarize you with something that I taught back in A2 Trig. So about half of you already know this, but the way I teach it is relevant to what I'm about to do. When I teach inverses, where you switch the x and the y and then you solve for y, you all remember doing that back in A2 Trig? I preach and preach and preach. I almost make it like a mantra where it's a cheer. I say inverse, you say?
Wait, what?
And everybody in the class yells switch. I say inverse, you say switch. And that way when I kind of do that little cheer, y'all know I'm talking about an inverse. So when you're doing an inverse, you're always going to be switching something. A multiplicative inverse is top to bottom. A graphical inverse is switching over the line y equals x. An algebraic inverse is switching the x and the y coordinates. And a graphical inverse is switching the x and the y coordinates in the point. So you're always switching something, and it does help to think of it as a switch because you know anytime I'm talking about an inverse, something's got to flip, something's got to change, something's got to get inverted. And so what we're going to be doing here is we're going to be talking about taking a derivative of an inverse. Now, to do that, I have two options. I can take the inverse and then derive it and plug in the number I want, or I can exploit the idea that an inverse is also a multiplicative inverse. And I can find the derivative first and then just flip it. Because it's the same thing. And that's scads and scads easier than actually finding an inverse. Now what I'm going to do is I'm going to prove to you that it does work by doing one or two of these things. And then I'm going to give you a step-by-step, this is what you're going to do. The biggest thing you need to know is if I'm going to do my little trick where I actually don't find the inverse and then derive, but rather derive and then invert, flip it upside down, literally multiplicatively reciprocate it. If I'm going to use that little trick, I need to remember that what they're giving me in terms of a number here, let's go down to this first example. The number that they're going to ask me to plug in is a number that they're asking me to plug into the inverse function. It's an x that I'm putting into the inverse function. And now you need to think backwards to what that number would have been in the original function. Because it wasn't an x. In the original function, if that number's an x in the inverse function, it was originally a y. And that becomes the biggest sticking point. Is if I'm going to do this little, don't find the inverse and then derive, but rather derive and invert, then this is not the number I want to be using. I'm going to be plugging into the derivative of the original function. I want to plug in the x for the original function, which I'll also have to find. Now typically that's a really easy find. If they're going to put it in the no calculator section of the test, it'll be uber easy. If they're not going to put it in the no calculator section of the test, it'll be a calculator question. So that's the issue. Let's go ahead and try this first one. Actually, I want to try one that's a slightly easier question. I am going to go to this question, and I'm going to copy it into my notes on a fresh sheet of paper so I can do this one with you. And we're going to try this question. That didn't copy. Please, if I say please, will you copy? Do I have to wait? 1, 2, 3, go? Yes, I had to wait. I was being impatient. So I'm going to do this two different ways. First, I'm going to find the inverse and then take its derivative. And then I'm going to derive it and then plug into it. Okay? And I am going to do that for what number? I am apparently going to do that for f inverse of 2. So I am going to find f inverse prime of 2. Now they can do that in a whole bunch of different ways. The inverse and the prime may be outside the entire function, but you're going to end up seeing both of those notations. There's an inverse notation there, there's a prime notation there. So that means they want you to both invert and derive. Plug in a 2. If you're going to do it the way they said it, which is I'm going to find the inverse and then derive it, then the number you'll be plugging in is a 2 because you'll be plugging that 2 into the inverse. So this is the original way. I'm going to go ahead and find the inverse. I say inverse, you say switch. Here goes. Now the goal here when I'm finding an inverse is to isolate the y. Now this is a little bit tricky because I actually have 2 y's, but we've done these before. I'm going to treat this like it's a fraction, and I'm going to cross multiply. I am actually physically going to distribute here. That's a 3x. I don't know why I wrote it that way. And then I'm going to get all the y terms over on the left and all the x terms over on the right. So I'll have xy minus y and 3x minus 5. So everybody see how I did that? Y'all still good? And I'm doing this algebra kind of quick because I want to get through it. And we're not going to frequently do it this way, but I want you to buy into this stuff. I'm going to factor out my y. And that step right there is how I take those 2 y's and narrow them down to a single y. Divide out that set of parentheses, and I now have my inverse function. And I'll call it 3x minus 5 over x minus 1. Now that's step 1. I found the inverse. Step 2. Take its derivative. So now I'm going to take the derivative of this thing. I'm going to dx it. When I take the derivative of that thing, I got to use the quotient rule. So the derivative of this thing, or f inverse prime of x, will become low d high minus high d low all over low squared. Still good? Now, since what I derived was legitimately an inverse, the 2 is what I'm going to plug in. So I'm not going to simplify this. I got a number. I'm just going to plug in a number. So I'm going to make every one of these x's be a 2. And I'm going to do a little math. So 2 minus 1 is 1 times 3 is 3. 6 minus 5 is times 1 is 1. And 2 minus 1 is squared is 1. This answer is a 2. We good so far? Now I'm going to try it the other way. You okay there? To do it the other way would have said to take this same exact question and first find the x value for which it is equal to 2. In other words, find the y value. Let me see if I can say this differently. This 2 that I'm going to plug into the inverse was a y value in the original function because I switched them. So since I want to plug an x value into the derivative, I need to find that x value first. So I'm going to do a little cross multiplying here. I'm going to subtract out a 2. I'm going to add 6 to both sides, and the x value that I'll be using is 1. Like I said, if they're going to put it on the no calculator part of the test, that finding of the x will be pretty super simple. Still good? Okay, step 2. I'm not going to find the inverse. I will never know the inverse. I have no care what the inverse is. I don't give a hoot. Because I'm not going to find the inverse function. I'm going to find the multiplicative inverse of the derivative. Am I finding a variety of inverse? Yes. Is it the one they intended? No. That's okay. So I'm just going to take the derivative of this thing. Still need the quotient rule. And the quotient rule would go low d high minus high d low all over low squared. I'm going to plug a number into this, but the number I'm going to plug in is not the 2 they gave me, but rather the one that corresponds to that 2. The x that went with the original y that they gave me because it was the x of the inverse. Okay? So I'm going to plug a 1 in there. So I'm going to make all of these x's be 1s. And I'm going to do some more math. A 1 minus a 3 is a negative 2 times 1 is negative 2, minus a 1